Uh, Good afternoon, guys. This is Professor David J. De Los Reyes. Okay, before I will discuss my topic for this afternoon, I will try to correct an error from the last lesson number. I think 85, right? 85. Under lesson 85, I got a syntax error on the final answer. For lesson number 86, this is an erratum. This is a correction, guys. The perimeter of a rectangle should be, this should be the correct one. I made a syntax error on writing the final answer. It should be twice the quantity length plus width units. What I wrote yesterday was that perimeter for a rectangle as a final answer is just 2 times length times width. This is wrong. I miswrote it. If you try to figure out my solution, it's only on the last portion that I made a mistake. So instead of writing 2 times the quantity length plus width, I write it as like this. This is wrong. Okay? And this should be the correct one. So actually, my lesson 85 was all correct except for the writing of the final answer. And the final answer for the perimeter of a rectangle should be twice the quantity length plus width. It is obvious. The perimeter is actually L plus L, that's 2L. And this is width, so this is 2W. Okay? So this one got no meaning, you know. This is wrong. Okay? I miswrote it. My computation was correct. Okay? If you try to follow the simplification, the mistake was on the writing of the final perimeter formula. And the correct one, this is an erratum, guys. Perimeter for a rectangle in general should be twice the quantity length plus width. Twice the length plus twice the width. This is the correct one. Okay? Oh, that's the correction of lesson number 86. So for those who are following my lecture, okay, you can comment on there, and if you notice the error, this will be the answer. Okay, let's proceed with my new lesson this afternoon. My new lesson for this afternoon on my channel will be lesson number 87, still on integral calculus, length of arcs. This afternoon, we will derive the perimeter of a square. Perimeter of a square. So, under lower mathematics, the perimeter for a square is actually 4 times the side. Right? 4 times the side. Because for a square, all the sides are equal. So obviously, the total distance going around is 4 times the length of the side. So we will derive this one. Okay, I will try to read the problem. Derive by integration the perimeter of a square. The designation of the side is actually small letter a. Meaning, if the side of the square is a, what will be the perimeter as a function of a? Okay, perimeter as a function of the side. And supposed to be what will come out will be this. Okay, let's try to bring out the solution. We drew the graph on the Cartesian coordinate system. It's a part of the solution. Y-axis, x-axis, first side, second side, third side, fourth side, it is a square. The coordinate of this corner here will be A0. The coordinate of this second one will be A and A, meaning the abscissa is A, the ordinate is A. This one, the abscissa is 0, the ordinate is A, so this is 0A. Fourth one, it falls under the origin, so the abscissa is 0, the ordinate is 0. Okay, that's the graph of the square on the Cartesian coordinate system. Okay, let's try to bring out the solution. Differential length of arc. The general equation in which I give you the past 2 lessons back. It is actually there is no Fourier. It will be, the first one will be differential length of arc, which is the square root of 1 plus dy dx quantity square times dx. Okay, this will be the formula that we will be using. Okay. You could use the second one instead of dx, it will be dy, but it will be the same. Anyway, the square is symmetrical. So you could either use the horizontal side or the vertical side. And since the figure is symmetrical, okay, I will try to use the horizontal side. So this is dx. If you try to notice the figure, it is symmetrical. So what will I do is that I will just take one length of this one side over here, okay, then times 4. Right? All the sides are equal. So if we try to get the distance going around, just take the length of one side, then multiply it by 4. But we need the equation of dy dx. Where will we get the value of dy dx? You should specify the equation of this line here, this horizontal line. Since we are using dx, we use this side here. Okay? And the equation of this side here, it is from analytic geometry, is y is equal to a. It is a horizontal line. For the meantime, we are not given y as a function of x. And luckily, we are given y as a function of a pure constant. Okay? There's nothing wrong with this because this one is simpler than this. Okay? So, if we try to bring out the equation of this, so that's from analytic geometry, y is actually equal to a. That's a part of the solution. No one is telling you to bring out this equation. It should come out from your mind. That's a part of analytic geometry. The derivative with respect to x of y equal to the derivative with respect to x of a. Taking the differential of both sides. So we will produce dy dx. The derivative with respect to x of y is just dy dx equal to the derivative with respect to x of a. A is constant. So the derivative of a with respect to x will be 0. Okay? Squaring both sides, dy dx quantity square equal to 0 quantity square. 0 square is just 0. Okay? So, sorry for that one. Since we now know the value of dy dx quantity square, we will take this value 0 here, we place it here. So we'll go back to this equation. Differential length of arc equal to, for the integral from 0 to a, and following this, the square root of 1. The square of the first derivative is actually 0, so this is plus 0 times dx. Actually, we are now integrating both sides. Okay. I place the upper and lower limit to be 0 and a. In here, I place it till I specify 0 is the lower limit, a is the upper limit. How is that so? To take the total distance of the top horizontal line, x should move from this point here to this, or same as this. So actually x here is 0, and x here is actually a. So this is the lower limit, this is the upper limit. That's why I place it here, 0 is the lower limit, a is the upper limit. So integrating both sides, the integral of the differential length of arc equal to, for the integral from 0 to a, I just repeat what I did a while ago, square root of 1 plus 0 times dx. The integral of the differential length of arc will be s equal to 4. The integral of, since this is 1, it could either be plus or minus 1, or this will just be simply 1 times dx. Or this should be the integral from 0 to a of dx. It seems this is just dx now, because the square root is just square root of 1. Okay? And luckily, the integral of the differential of x, it's an easy money. It is x. So this is 4. The integral of the x will be x with the limit from 0 to a. Substituting the upper and lower limit, this should be 4 times the quantity a minus 0. Upper limit, lower limit. Okay, let's be careful with this one. So what will come out is actually, that's our mistake yesterday. We go abruptly in writing the final answer. Let's try to bring out the simplification first. This is 4 times a minus 0 is a. 4 times a is equal to 4a. We should have done like this yesterday, so we don't commit mistake on writing the final answer. So actually the final answer is S equal to 4 times a units. Units, it's just a unit length. The distance going around is a unit distance, so this is units. So actually I could now replace this S here as what do you call this? Sorry for that one. It should be P. P refers to perimeter. So for a square, the perimeter is actually 4 times the length of the side units. So whatever the length of the side of the square, you multiply that by 4, that will be the perimeter. So the formula we are using under lower mathematics, in which the perimeter for a square is 4 times the length of the side, is actually emanates from integral calculus. It all was derived from integral calculus. Okay, so we now know the formula for taking the perimeter of a rectangle. I repeat it. Twice the quantity length plus width units. And for a square, it should be 4 times the length of a side units. Okay, good afternoon, Los Angeles.